Swayam Prabha. Digital India. Educated India.
One such civil structure is known as trusses, and we will see how do we analyze them and determine the forces acting at various members in order to predict the performance of such structures. The picture accompanying this slide shows a typical truss used to support bridges. Other examples are the roof supports, the derricks, the structures used to support the radio antennas and high voltage cables. All these trusses have one common characteristic, that they constitute of only straight members and they are connected at their extremities. As you see in this example, you have many straight elements which are connected at their extremities only. Let us see this example little more clearly. This picture shows a part of the bridge. So, this is the bridge platform which is supported by beams, and these beams are supported by the trusses. So, here you see one plain truss in the front and another plain truss at the rear. Plain trusses are trusses whose elements lie in a single plane and their loading is also in the same plane. So, the problem can be analyzed as a two-dimensional problem. So, let us take one of these trusses, let us say the front set of elements, and that is shown in this picture. Here we see that the loads are carried by these beams and they are transmitted to the truss through these joints. So, that is what you see in this picture as the various loads P1, P2, P3. So, one thing that we observe is that all these external loads that are applied on the truss is applied to its joints only, and we have seen that the truss constitutes of many linear elements, straight elements, and connected at their extremities. For a better analysis, we may have to also include the weight of the truss for better prediction of the internal forces. These are the supports. We have one support at A and another support at B. Typically, a truss is supported by a pin joint and a roller joint. A plain truss is supported by a pin joint and a roller support. This comes from our understanding of the basic equilibrium of two-dimensional objects. From the equilibrium equations, we can determine three unknowns. So, it is possible to determine the two reaction components, that is, let us say Ay and Ax, as well as one vertical component, that is By, at the joint B. Some other things that you may have to remember is that these members being slender, they cannot support lateral loads. That means, we cannot apply a load at this point, and the loads have to be only applied at the extremities, that is the joints. And we see that the truss is predominantly a structure which constitutes of such slender members which are two force members and the pins. This member is a two force member because each member has two joints, and if a member has to be in equilibrium, those two forces have to be collinear and it has to be along the axis of the element. Usually the members are designed with uniform cross section because it is possible to manufacture a bar stock of a uniform cross section and cut them to the required length to construct the entire truss. The weight of the members is negligible compared to the externally applied load, but for better analysis we can consider the weight of the member to be equally distributed at their joints. Let us say the weight of the member CE is equally distributed at joint C and joint E for an accurate analysis. Before we proceed to analyze the structure, that is the truss, we have to see what kind of loadings occur in the individual members of the truss. We have seen already that these members are two force members, and thus they can either be subjected to a tensile force. This picture shows that tensile loading. You have the two pins connected at the extremities of this two force member, and the externally applied load or the loads from the other connected members pull this member at the two joints. So, in order to resist the deformation, the member develops an internal force which tries to keep the various parts of the member in equilibrium, and thereby these forces pull the member towards itself. That is, at the joint, the internal force is acting away from the joint. The other kind of loading that is possible is the compressive load, where the external load or the loads from other members push the joint, thereby the internal force developed in the member is towards the joint. So, when we consider only part of the member in a free body diagram, one has to keep these directions in mind in order to construct the proper force directions in a free body diagram. Before we proceed to analyze the structure, one has to understand what we mean by a rigid truss. So, here we see the most simplest form of a truss, that is three elements AB, BC and AC connected at A, B and C, and the truss is supported by a pin joint at A and a roller joint at C. If we consider any two-dimensional element and which is not constrained, it has 3 degrees of freedom in this plane, that is, it can translate in the x direction and in the y direction, and it can rotate about the z axis. So, each of the two dimensional element has 3 degrees of freedom. So, if we connect another member, let us say the first member is AC and we connect it with another member CB, then 2 of its degrees are arrested. So, if we have 3 such elements connected at their extremities, out of the 9 degrees of freedom, that is 3 degrees of freedom individually for each member, for each of these joints 2 degrees are arrested. So, 6 degrees of freedoms are arrested. The remaining degrees of freedom that this combined structure has is 3. So, these 3 degrees of freedom have to be arrested by external supports, and that is what we see, that at A we put a pin connection. So, thereby it offers both reaction component AY and AX to arrest any translation, and the rotation degree of freedom is arrested by providing a roller at C. So, we see that this combination, that is 3 elements AB, BC and AC connected at 3 joints, is clearly a rigid element which does not undergoes any deformation when some external forces are applied. So, here we see an example of a truss which is not rigid. Here we see these members AB, BD, CD and AC connected at A, B, D and C and supported by a pin joint at A and a roller joint at C. But under the action of this external force at B, this truss element deforms because sufficient number of degrees of freedoms have not been restrained. So, when we design trusses, we have to design the truss to be rigid under the action of external forces. Here we see an example of an over rigid truss. And in an over rigid truss, the rigidity of the structure is not affected even if we remove, let us say, one of the elements. Let us say if we remove this element BD, then also we see that the structure does not deforms under the action of any load, let us say at D or at B. In order to optimally design a truss, we have to design trusses which are just rigid. That means sufficient number of degrees of freedoms have been arrested and we do not have additional members which, if we see in terms of economics, is not viable. So, here we see an truss which is just rigid. Here, even if you remove one of the members, either BD, CD, the rigidity of the truss is lost and the structure deforms under the action of any external loads. and we are interested to design such kinds of trusses which are just rigid. Let us see what we mean by simple trusses. The triangular truss that we have just seen, that is, we have this element AB, BC and AC connected by a roller at A and by a pin joint at A and a roller at C. This truss element is a rigid truss and it is known as a simple truss. If we add two more members and a joint, then this structure is also rigid. That is, we replicate this combination of the elements and joints which form a triangular pattern, and if this is replicated in this plane, we get simple plane trusses. These trusses have one property, that the number of members, if we designate it as m, is equal to 2 times the number of joints. If we have designated it as n, then 2n minus 3. So, let us see for this example, we have 3 plus 2, that is 5 members and 4 joints. So, 2n minus 3 is 8 minus 3, which is 5. So, this equation is valid, and such kind of trusses are statically determinate. Why do we say that they are statically determinate? Internally is that if we analyze this structure and we want to determine all the internal forces, then the number of unknowns that we have to determine is equal to the number of members, that is 5 in this case, plus the external reactions that we have to determine, that is 3, 2 reactions at the pin and 1 reaction at the roller, totaling to 8 unknowns. If we consider the free body diagram of a single joint, let us say joint D, then for the joint D to be in equilibrium, the sum of all the forces has to be 0. The moments are obviously 0 because all the forces are concurrent at D. So, these forces does not cause any moments, and so the summation of moment is obviously 0. But for the joint D to be in equilibrium, the summation of the forces have to be also be 0, and in 2D this results in 2 equations, that is summation of the horizontal component of the forces and summation of vertical component of the forces. So, for each joint from the free body diagram, one can determine 2 unknowns. So, if we have n number of joints in a truss, then we can determine 2n number of unknowns. So, for the problem to be statically determinate, the number of unknowns, that is m plus 3, should be equal to the number of equations that we can write, that is 2n, and that is what this equation depicts, that m is equal to 2n minus 3. If we extend this discussion to 3D, then a simple 3-dimensional truss is a tetrahedron constituting of 6 elements connected at 4 joints, that is A, B, C and D. Initially, we will see analysis of simple plane trusses. The internal forces of the trusses can be determined by 2 methods. One is known as the method of joints and the other the method of sections. Initially, let us see how to determine the forces in various members by method of joints. As the name suggests, the method primarily relies on determining the internal forces from the equilibrium equations of constituent joints. So, let us see the procedure. Initially, we determine the external reactions at the supports by considering the free body diagram of the complete truss. Obviously, we assume that the structure is externally statically determinate. That means, it is possible to find all the external reactions. Next, we consider the free body diagram of each of the joints or pins, and we show the external forces as well as the forces exerted by the supports and the forces exerted by various members connected at the joints in the free body diagram. Here we will see that for a plain truss, if we have m number of members, then we have m number of unknowns plus 3 number of external reactions to be determined, and the number of equations from the end joints will be 2n, and thus for the problem to be statically determinate, m plus 3 should be equal to 2n. In 3D, we see that the force summation equation at each joint results in 3 scalar equations. Thereby, we can determine 3 unknowns for each of the free body diagram from the joint. So, the number of unknowns, that is the number of members in the truss, plus the number of unknown reactions, that is 6 in case of 3 dimensional trusses, should be equal to 3n for a space truss. Obviously, here we should remember that these equations are not independent of the external equations used for determining the external reactions. Few more points to be noted are that if the geometry of the truss is known, then the direction of all the internal forces, that is the forces that exist in each of the members, is also known. Only the magnitude of those forces is unknown. And in case of simple trusses, it is possible to draw the free body diagrams of the joints such that at any instant we only have 2 unknowns. So, thereby we do not need to solve simultaneous equations, rather we can solve at a time only 2 unknowns from each of the equations from each of the free body diagram. The forces can be obtained from these equations, and one can also perform checks as we proceed. Before we proceed to analyze, we have to assume the nature of the internal forces that are existing. We have already seen that the forces can be either tensile in nature or compressive in nature, and we have to assume either of this and accordingly depict the same. And after solving, if we find that the answer turns out to be negative, then we can update the assumption. That is, if we have originally assumed that the member is in tension and the answer turns out to be negative, then the member is in compression. Finally, we present all the determined forces along with the nature of the forces, that is either tensile or compressive. So, let us see the complete procedure with an example. Here you see a truss, a plain truss supported by pin at A and roller at D, and some external forces applied at joint F and E. The procedure starts by first determining the external reactions, that is the reactions at A and D. In order to determine that, we constitute the free body diagram of the complete truss. So, at A we replace the pin joint by two reaction components AX and AY, and at D the roller is replaced by a single vertical component of reaction dy. And since we have only 3 unknowns, and from 2 force summation equation and 1 moment summation equation, the 3 unknowns can be determined. So, we have taken in this case the moment summation about point A, which gives the value of dy, and the 2 force summation equation, that is sigma Fy and sigma Fx, give Ay and Ax. In this case, Ax is 0 and Ay is 8.75 kilonewtons and dy is 6.25 kilonewtons. Once these external reactions have been determined, we can proceed to determine the internal forces. In order to determine the internal forces, we should first consider a joint where only 2 forces are unknown. So, we can consider this joint A, where we have only 2 members, that is AB and AF, and thus 2 unknowns, that is force in the member AB and force in the member AF. Here we assume that all the internal forces are tensile in nature, thereby these vectors are pointing away from the joint A. From this free body diagram, we can write the 2 force summation equation, that is summation of all vertical components should be 0 for equilibrium and summation of all horizontal components should be equal to 0. Summation of vertical component is the vertical component of force in AB, that is FAB, sine of this angle, that is the angle between the member AB and AF, which in this case from the geometry is 4 by 4.472. So, FAB sin theta plus the vertical component of reaction, that is AY, which is 8.75, should be 0, which gives that FAB should be equal to minus 9.78 kilonewton. Since the answer has turned out to be negative, our original assumption was that the member AB is in tension, but since the answer has turned out to be negative, the member is actually in compression. So, the force in the member AB is 9.78 kilonewton compressive. Now, this equation, which is the force summation along the x direction, gives the force in AF. Now, we can move to another joint where again we have only 2 unknowns. Let us consider the joint B. If you remember the geometry, we have the members A, B and F and C, and this force has been determined already. So, now if we write the force summation equation, then AB, if this angle is theta, then AB cos theta plus the force in the member BF should be 0, and sigma Fy gives AB sin theta plus force in the member BC equal to 0. This results in determining the force in the member BF. So, now we can move on to the next element, that is F. Since we have already determined the force in BF and AF, we can now determine this force in FC and FE, because now at this joint, at this instant, at joint F we only have two unknowns, and the two equations gives the values of force in FC and force in FE. Similarly, one can proceed to all the joints in order to determine the various internal forces. Let us see another example. Here we have this truss element A, B, C, D, E connected at A and C by pin joints. Is this problem externally statically determinate? If we consider the free body diagram of the complete truss element, that is A, B, C, D, E, and the external forces of 6 kilonewton applied at B and 3 kilonewtons applied at E. At A we have a pin connection, and so we have to determine two components of reaction AY and AX, and at C we again have a pin reaction, thereby we have to determine the two components of reaction CY and CX. So, the total number of unknowns at hand is AX, AY, CX, CY. But we know that for this truss to be in equilibrium, if we write the force summation equation, sigma Fx equal to 0, sigma Fy equal to 0, and sigma moment, let us say about a point A, to be equal to 0. These three equations can be used to determine only three of these unknowns. So, how do we proceed? If we see that if we remove this truss from its support, actually this element CD is no longer rigid and is free to rotate about this joint D. So, we cannot consider the complete truss to be rigid, but rather we have to consider the two individual elements that is AB DE and the single element CD as two separate rigid bodies. So, now for each of this free body diagram, let us depict what are the unknowns. At A we do not know the two components of reactions, that is AY and AX. At D we do not know the two components again, that is dx and dy. If we come to this element CD, at C it is connected by a pin. So, again we have two unknown components of reaction, that is Cy and Cx, and at D we have dy and dx. We can observe that since this D is the common joint between this element and this element, the forces are equal and opposite. So, what are the unknowns? We have Ax, Ay, dx, dy from this free body diagram, and Cx, Cy from this free body diagram, because this dx and dy are equal in magnitude and only opposite in direction to these two forces. So, now we see that we have 6 number of unknowns to be determined, and each of the free body diagram, if I designate this as free body diagram 1 and this as free body diagram 2, FBD2, then from these two diagrams we have 3 plus 3, that is 6 equations, and we have 6 unknowns to be determined. So, this problem now becomes statically determinate. Once we have determined these external reactions and the force at D, now we can use the method of joints to determine all the internal forces. Let us see a 3-dimensional truss example. Here you see a 3-dimensional truss A, B, C, D, E subjected to an external load of 2L at A and a load of L at D, and it is supported by a pivot joint at B and by slender members at E and C as well as at D. First, let us see if this problem is statically determinate externally. In order to do that, we have to construct the free body diagram of this truss. Since at B the truss is pinned, it arrests all translation and thereby provides 3 components of reaction Bx, By and Bz. And at C we have an slender vertical rod, thereby the member can only support a vertical reaction and thus offers only a vertical component of reaction Cz. Same is the case at joint E, where we again have a slender member. At D we have a horizontal member along the y direction and thereby we have a single component of reaction dy. So, we see that we have total of 3 plus 3 6 unknown reactions to be determined, and from the free body diagram of the complete truss we have 6 equations, that is 3 force summation equation and 3 moment summation equation. Thereby it is possible to determine all the reactions. But let us see this problem. Here we are just interested to find the force in the member BD. So, in order to determine the force in this member BD, we can either consider the equilibrium of this joint or the equilibrium of this joint, and the only criteria that has to be satisfied is that since in 3D from the force summation equation we can determine 3 unknowns, At a joint, we should only have 3 unknown components of force to be determined. If we see the joint at B, we have to determine 3 unknown reactions and then the various forces, that is BC, BD, BE and BA. At D, we have to determine only one external reaction dy and the forces in the members AD, CD, BD, ED, etc. At D, we see that we have to determine 4 members, forces in 4 members, and in order to do that, we need to know at least one force if we have to use the equilibrium equation of joint D. So, we see that if we can determine the force in this member CD, then the problem can be solved, and in order to find the force in member CD, we have to know this external reaction CZ. So, we see that in order to determine the force in this member BD, it is sufficient to determine these 2 external reactions, that is dy and CZ. So, this can be determined by using the moment summation equation. So, here we use the moments about this axis BE, which provides this reaction CZ, and the moment summation about the vertical axis passing through B, that is BZ, results in determining this reaction dy. Both have turned out to be L. Now, we can proceed to determine the force CD by considering the equilibrium of this joint C. So, here you see the joint C with various forces, that is FCB, FCA and FCD. The direction cosines of these forces can be determined from the geometry of the truss. Particularly for determining this direction cosine of the member CA, you have to consider the geometry of the truss, and it has been determined to be 0.359 in the negative direction of I and 0.35 times in the j direction and 0.862 in the k direction. So, this gives the unit vector along this member CA. So, the force in this member CA is equal to the magnitude of the force times the unit vector along the direction of the member. And since now we have determined all these forces in their vector form, now we can use the equilibrium equation to determine the forces. So, the equilibrium equation sigma f equal to 0 results in 3 scalar equations, one for I, j and k, one each for I, j and k. Since we are interested in determining this force in CD, we can solve these 2 equations to determine the force in CD, and it has been found to be 0.417 times of L. Now that we have determined this force, we can move to this joint D. The various forces, both internal as well as the external reaction and the externally applied load, are shown in this picture. The direction cosines of various forces can be obtained from the geometry of the truss, and we have already determined the magnitude of this force in member CD, and so we have 3 unknowns, that is the force in BD, force in the element ED and force in the member DA to be determined, and these can be determined from the force summation equation. The 3 scalar components gives the 3 equations, and one can determine the force in the member BD. So, this example shows the complete working procedure by method of joints for solving the problem of determining the internal forces in the trusses. Sometimes special conditions help in expediting the analysis of the truss. So, if we can determine such special loading conditions a priori to solving the problem, it makes the solution procedure simpler as well as gives scope for doing additional checks. One kind of special loading is known as the zero force members, and this picture depicts a truss element, that is A, B, C, D, E, F, connected by a roller at A and by a pin joint at F, and various externally applied loaders like F1, F2, F3 at joints C, E and G. Let us consider this equilibrium of this joint at B. We have this force in the member BC, FBC. Since the member is horizontal, the force is along the x direction, and the force in the member AB, that is FAB, is along the direction. So, if a force exists in this member AB, then it will have a vertical component and a horizontal component. The horizontal component of this force AB can be balanced by a force that exists in, let us say, the member BC, but the vertical component of this force FAB cannot be balanced because this member BC, which is horizontal, cannot support any vertical component of the force. Since the vertical component of this force cannot be balanced, the force in this member has to be 0, and if the force in this member AB is 0, then there is no horizontal component of the force AB, and thereby the force in BC has to be also 0. So, we find that the force in the member BC as well as the force in the member AB are 0 because of this geometric configuration. Let us also see the joint D, which occurs in the same truss. Here we have two elements CD and DE, which are horizontal, and we have this element DG, which is inclined. For equilibrium to exist and for this joint D to be in equilibrium, the vertical component of this force DG has to be balanced, and since both the members CD as well as DE are horizontal and cannot take any vertical component of the force, the forces in the member DG has to be 0, and the force in member CD is balanced by the force in member DE. So, it is possible to determine using this analogy the various zero force members if it exists in a truss. There is another special configuration that we call it as the redundant joint configuration. That is, in a redundant joint, the forces of the constituent members are not shared. Like here you see this black member and the blue member, which are collinear, as well as the red member and the pink member, which are again collinear, connected at this joint. But we see that for equilibrium there is no load sharing, that is the force in this member F2 is balanced by the force in this blue member F4, and the force in this red member F1 is balanced by the force in this pink member, that is F3. So, this joint does not takes part in the load sharing. So, thereby the presence of this joint is a redundancy and it does not helps in load sharing between the members. So, if we can determine such special conditions that exist in a truss, it generally expedites the process of determining the internal forces. Let us see one example. Here we see a plain truss which is connected by a pin joint at A and a roller joint at O, and some external forces P and Q are applied at joints E and N. The problem is statically determinate because we have only three reaction components to be determined, and from the free body diagram of the entire truss it is possible to determine the same. Let us see if we can find some special loading conditions, that is either the zero force members or the redundant joint in this truss. Let us analyze this joint B first. This member BC from the geometry of this truss is perpendicular to AB as well as BD, and thus for the equilibrium to exist, for the joint B to be in equilibrium, if we consider the force summation along BC and AD which are perpendicular axes, the force in AB is balanced by the force in BD, but the force in BC is not balanced because we do not have any member to balance the force in this member. So, since there is no member which can take the force in BC, the force in BC has to be 0. So, the same analogy can be used for this joint at F, where we have DF and FG collinear and DF and FH collinear and FG which is perpendicular to DF and FH. Using the same analogy and discussion, this force in FG is to be 0. We can again see that we have a similar configuration at J, where HJ and JL are collinear and IJ is perpendicular to both HJ and JL. Thereby, this member IJ has to be also a zero force member, but this discussion does not holds valid for this joint N, because we have an external force Q applied at N. Here this element Ln and NO are collinear and Mn is perpendicular to the same, but since we have this external force Q acting at N, the forces in all these three members are not 0. Now, we have determined that this force in BC, FG and IJ are 0. So, now we can see other joints if the special condition exists in the constituent members. Let us move to this joint at C. We have already seen that this member BC has to be a zero force member and AC and CE are collinear. So, if a force exists in this member CD, then its vertical component cannot be balanced, and this renders this member CD to be also a zero force member. Same way, if we analyze this joint at G, we have this force in this member FG is 0 and this member EG and GH are collinear, and if a force exists in DG, it cannot be balanced because we have already determined the force in FG to be 0. So, thus we see that this member DG as well as DC are also zero force members. If both DC and DG are zero force members, then obviously this member DE has to be also a zero force member, because any force in BD is balanced by the force in DF, but the force in DE cannot be balanced. So, we see that these members DC, DE as well as DG are zero force members. And if we analyze this joint I, we can find that IL is also a zero force member. So, all these zero force members are marked in red in this picture. And once we have determined these zero force members, now if the problem was to determine all the internal forces of the various members, then we can only consider those joint equations which results in determining the various unknowns. So, in today's lecture, we have seen how to analyze the trusses by method of joints to determine the various internal forces that exist in the members of the truss. In the next lecture, we will see how to analyze the trusses and determine the internal members by the method of sections. In the method of joints, in order to determine, let us say, a force in an element, one has to successively solve for equilibrium equations of various joints till one determines the force in a particular member. In cases where we are interested only in determining a force in a single member or few members in a truss, the method of joints is not an efficient method, and here the method of section comes to help analyzing the problem quickly to determine only those forces that are of interest. We will see this method in the next lecture.